Thousands of years ago, the Greeks and Egyptians adopted the human foot as the first known unit of measure. But whose foot should set the standard? King Henry I declared that a yard should be defined as the distance from the tip of his nose to the end of his thumb. The invention of the metric system in 1790 improved matters somewhat by basing units of measure on more widely agreed upon standards, like the circumference of the Earth. Back at the turn of this century, Lord Kelvin, namesake of the International Temperature Standard, said it best: "One has but a poor understanding of that which one cannot measure." Today, we try to have rational, simple, and consistent measurement systems based on sound scientific principles. The goal of this video series is to introduce you to the principles of measurement, but we'll also show you some of the standard techniques and equipment. The series is designed as a basic introduction to measurement. It should help you whether you are attempting to learn about measurement as training for a new job or you're trying to solve a particular measurement problem. The series may not give you all the answers, but after watching, I hope that you will at least be able to ask the right questions. I've come to the NOAA research vessel Albatross 4 at its home port in Woods Hole, Massachusetts to talk about fluid quantity and flow measurement. The Albatross actually has a long history of innovation. The original Albatross was in fact the first vessel or ship ever to have onboard electrical power, and the light bulbs in that ship were installed by Thomas Edison himself. Now, the current mission of the Albatross is oceanographic research, and it's a good site to talk about fluid quantity and flow measurement techniques. Liquids and gases are both fluids, and we can use similar techniques to measure both. This is an example of a small handheld anemometer, which uses a small propeller to measure airflow. As air flows through the device, it spins the propeller and gives you a readout here. Now, a similar technique is used in one of the experiments here on the Albatross. This is a set of plankton nets, which are called bongos by the scientists, and they're used to measure the density of plankton at different levels in the ocean. The way they're used is that the nets are towed through the ocean for a fixed period of time, and plankton is collected in the back of the nets. In order to know what the density is, you need to know how much water you pulled the nets through. So we have a flow sensor here in the throat of the net, which measures the flow through the net. I have an example of one of the flow sensors here. And you can see, again, the way it works is that as water flows by the device, it spins a small propeller here. Actually, it spins this way. And the number changes every time the propeller goes around. Then what we do is we've calibrated the device so we know what the integrated flow rate is, or integrated flow. So this is used to calculate how much water has actually gone into the net. Now what I'd like to do is go up to the bridge and talk about some techniques to measure the quantity of liquids. Let's start talking about the measurement of quantities of fluid. Now, quantity is really mass. However, Here on the Albatross, we measure the quantity of fuel on board the vessel in units of gallons, which is a measurement of volume. Now, this is commonly done, and the mass of the fuel can be related to the volume through the density. Mass is equal to volume times density. So this works well as long as we know the density of the fuel or fluid we're trying to measure. However, if the fuel temperature changes, the fuel will actually, if say we heat it up, the fuel will expand and change the calibration between mass and volume. So you'll sometimes see quantities of liquids reported in volume units, say gallons or liters or other volume units like a cup of fluid. And you also see quantities of fluid sometimes reported in mass units, either kilograms or pounds. Because gases can be compressed, we can't use volume techniques to measure the quantity of the gas. So in fact, we use the fact that they're compressible to measure their quantity. In the scuba tank here, the mass actually does change when I fill up the tank. So if it was full, it would sink in the ocean here, and if it was empty, it would float. But I need a more accurate method. Now what I do is actually use the relationship between pressure and mass. If this were an ideal gas in the tank, the pressure times the volume of the tank is equal to the mass of gas in the tank times the temperature times a calibration constant. So that's actually what I do. And in fact, if you look on the regulator, there's a small pressure gauge. And I've pressurized it. There's about 900 pounds per square inch of pressure in the tank. Because the maximum amount of pressure in the tank is 3,000 pounds per square inch, you can see that this tank is actually almost empty. One simple method for measuring the quantity of the liquid is by the use of calibrated volume techniques. I have here a couple of simple examples. This is just a measuring cup, which has got calibrated volume. This is a graduated cylinder, and this is a calibrated beaker. Now, the way you make the measurement, say, on this graduated cylinder is by looking at the height of the column of fluid, and you can see that there are measurement marks. This particular cylinder is calibrated in milliliters. Now, you can run into some problems with the measurement. For example, if you look very closely at the boundary between the liquid and the air, you can see that the fluid tends to run up the side of the cylinder due to the surface tension, or what we call the meniscus. So you actually make the measurement at the flat part of the fluid, and you have a small error due to the meniscus. Now, if we were to try to use this cylinder on a moving vessel like the Albatross here when we're at sea, you'd run into a problem. If you look over my shoulder, you can see there's an inclinometer that shows that the ship will have a tendency to roll and pitch. The inclinometer is calibrated up to 50 degrees, but it would be very actually dangerous if we went over that far. But it's not uncommon to roll, say, 10 degrees. Now, if I look at the cylinder and roll it 10 degrees, left and right, you can see that it becomes unclear as to what the measurement is. The measurement's ambiguous, so I either have to sort of average the measurement or tilt the cylinder to level out the fluid again. Another thing that can happen in a moving vessel like a ship or a helicopter is the shaking of the vessel. The vibrations can cause sloshing of the fluid, making a difficulty in making the measurement. Now, for smaller volumes, I can use a similar technique. This is a pipette. What I can do is I can draw a fixed amount of fluid up out of the pipette. Okay. This particular one, again, is calibrated in milliliters. Okay. And you can see I actually have a problem because I got a little bubble that went up into the pipette. So that bubble will create an error in the measurement. And let me demonstrate that a different way. Let me just get the fluid out of here. If I use the graduated cylinder and now make a measurement of a more difficult fluid, let's take this Coke here and pour it in the cylinder, you can see I run into another problem.